Welcome back to Think Thrice Problem Solving. Today we're going to be solving a fun little problem that has a interesting nested root thing going on. So we want to find an expression, so a way to describe this set of infinite radicals in some simplified expression. So if you want to give this a shot, go ahead and pause the video. Otherwise, we're going to jump straight into a solution. So what we're going to do here is we're going to try to get it out of this current format. This is a little bit ugly right now. So what we're going to do is we're going to rewrite this. And notice that we have 2 raised into the square root. So that's the same as 2 to the 1/2 power. And then this 2 right here is inside a cubed root and also inside a square root. So this is going to be 2 to the 1/3 times 1/2. Sorry, that got a little bit messed up. And then I have this 2 right here. This is inside a 4th and a 3rd and a square root. So this is going to be times 2 to the 1/4 times 1/3 times 1/2. And I'll be able to continue this as we go to the right. So what do we notice? I can combine all of those exponents, and I can rewrite my expression as 2 to the 1/2 plus 1/3 times 1/2 plus 1/4 times 1/3 times 1/2, and so on. And that'll just keep going over to the right. And what do I notice about these expressions? So there's a pattern to them, obviously. So I have 1/2, then 1/3 times 1/2. And what I'm noticing is that in the denominators, I'm getting 1/2 factorial, then 1/3 factorial. So remember that factorial is 3 times 2 times 1. 4 factorial will be 4 times 3 times 2 times 1. So I'm getting this pattern that looks like it's going to just continue as we move to the right. So my real question is, if I want to express this in a simplified form, what on earth is this set of inverse factorials over here? So is there another way that I can describe that? So what this really becomes is this red box is going to be equal to the sum from n equals 2 to infinity of 1/n factorial. So that's what I want to figure out. So if you've done some calculus in the past, you'll notice that this thing looks a little bit familiar. So this looks a little bit like our Taylor series approximations. So what a Taylor series is, it says that, and they don't always converge, but we'll take a look at this one. So if we have a function f of x, then that can be approximated in this way, where we have n equals 0 to infinity of the nth derivative evaluated at 0, divided, this is technically a Maclaurin series because we're evaluating at 0, divided by n factorial times x to the n. So what does that look like? Essentially what we're doing is we're saying f of x can be approximated with an infinite polynomial. So this will be f of 0 plus f prime of 0 over 0 factorial, which is 1, times x to the 0, plus f double prime of 0, or sorry, over 1 factorial. This is technically over 0 factorial, which is 1. This would be over 2 factorial. And then I'd have the third derivative evaluated at 0. And this is times x. This is x squared. This would be over 3 factorial times x cubed, and so on. So our real goal, so if we look at this, it looks a little bit like this up here. And essentially what we do when we create a Taylor series is we basically say at 0, we want to have our function matching. So we're going to make this guy match just our function. Then we're going to make the first derivative match, then the second derivative match, and the third derivative match. And you'll notice when you take the third derivative of x cubed, we're going to get x to the, we're going to get 3x squared, then 3 times 2x squared. So that's where this comes in to negate that. Or not negate, to cancel out. Okay. So our real goal is, so what we notice is that if x equals 1, then this looks like the sum from n equals 0 to infinity of f to the nth derivative of f evaluated at 0 over n factorial, which is really, really close to what I have up there again. Okay, so my question now to you is, what function evaluated at 0 is always 1 regardless, I don't know why I'm writing so much, of the derivative? Okay, and while that's really unclear, so I mean f of 0 equals 1 equals f prime of 0 equals f double prime of 0 equals so on. So if you think for a second, hopefully you can come up with, there's only one real function that matches that, and his name is e, and he's kind of specially designed. So e to the x, and we know that e to the 0 is equal to 1. E to the x, our derivative with respect to x, is also e to the x. So we're just going to keep getting the same function. So we can see that e to the x is equal to f, so e to the 0 plus e to the 0 over 1 times x plus e to the 0 over 2 factorial times x squared plus e to the 0 over 3 factorial times x cubed, and we just keep on going to the right. So all of these e to the 0's are just 1. And if I want to evaluate, so if I evaluate at e of 1, then that's going to equal 1 plus x would just be 1. So I'll circle that 1 because that's where I'm plugging it in. Plus 1 over 2 factorial times 1 plus 1 over 3 factorial times 1, and so on. And what we notice now is that I now have almost what I started with up here. So remember, I have this sum of just the factorials. So what we have now is e to the 1 is equal to 2 plus, and then the thing I was looking for, 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so on. So if I call this guy just a, how do I solve for a? It turns out that a is just equal to e minus 2. So what does that tell me? Well, that tells me everything I need to know, because up here, this was just 2 raised to that a. So my final answer for my expression in simplified form is going to be that whole big radical thing above is going to equal 2 to the e minus 2. And that is my final answer. Hope you enjoyed working through this problem with me. If you did, please like and subscribe. If you have your own problem you'd like me to try, go ahead and send it in. And as you're working through problems on your own, think once, think twice, and if you really get stuck, think thrice.